So, all right, we are on chapter 10 now. We got one slide through it last time, so we might as well just go and redo that slide. Why not? So, definitely start reading chapter 10. This is some important stuff, some very important words we will get through in this chapter, potentially today. So yeah, we were taking a bunch of random samples. That's the fancy technical term. We were trying to draw randomly from like a bag of things. That was our np.random.choice stuff from last chapter. Um, the technical term of what we were doing is we were sampling from a bunch of individuals, from a population. And so that's what was going on. All right, so there was a population that we cared about, like sides of a die, people on the Titanic. It doesn't have to be actual people like it was for the Titanic. Could have been the sides of a die, could have been the numbers on a roulette wheel, stuff like that. But a lot of the time, there's like a bunch of people that we really care about, like the entire population of the U.S. or something, that we can't just go and ask everybody who lives in the country some question. So what we do instead is we take a small sample and we try to make inferences about the original population. Like, all right, let's go get a bunch of like if you want to predict the outcome of an election, you're going to take a small sample of U.S. citizens that are of voting age, and you're going to try to infer like what everybody else is going to do. That's how that works, right? They don't ask everybody; they ask a few people, and usually they're pretty accurate, right? And so we also have to pick like how do we choose this sample? And that's kind of where we're starting today. So there's a couple different kinds of samples. There's easy ones, there's hard ones. We like them to be random, but they don't have to be random. The opposite of a random sample would be one that's called deterministic, like it's always fixed, it's determined. There's no chance involved at all. So I showed that to you last time. That's where we stopped, kind of. Like here's the Pokemon table. We read in the Pokemon table, and if you say .take on your Pokemon table, if I should just say like Pokemon take, I don't know, index 5. That's like the 6th Pokemon, and that's always, if I keep rerunning this, it's always going to take the 5th Pokemon on the table, right? You can also give it an array of like, take exactly these indices from the table, and it's always going to be Bulbasaur, Charmander, Squirtle, and Pikachu, all right? If I rerun it, it's still those. So that's a deterministic sample I have fixed up front what I'm getting. And so you can't really make many good conclusions from a deterministic sample. I hope you can understand that and agree with me on that, right? So we would like to instead have random samples, and that is when things are left to chance. Maybe not everything, but most things. So before you draw your sample out of your population, you have decided on the probability that each person gets picked. So it's still a random sample if, like, say I want to pick somebody from this class. If I pick with a slightly higher probability, like 75% chance I'll pick somebody on this side, 25% chance I'll pick somebody on this side, it's still random. But it's not uniform. There's a difference there. It's still a random sample if you know the probability that every group or every individual is going to get drawn out. It's okay if there's not an equal chance. It still counts as random. Just like if I got the left half of the class, not as often as the right half of the class. That's okay. It's still random. I'll still flip a coin, and if it's like 75% chance I'll go over here, 25% chance I'll go over there. Still slightly random, all right? But I think you can imagine we would like everybody to have equal chances. There's a different word for that, all right? But that's technically more side conditions. It's random already if you just know the probabilities and you still pick randomly according to those probabilities. There's also, this is still kind of like, this is neither deterministic nor random. We talked about this and then we ended last time, right? It's like, I would like to, if you go and interview somebody like on a street corner, like everybody who passes a street corner or everybody who passes by our door, that is neither deterministic nor random because it's going to be like a bunch of people walking by, right, every time. But at the same time, there's some certainty about like who's going to get picked, right? It's only going to be students, and so it's not going to be the entire population of Fresno County or something, if that's what you're trying to get at. So that's called a sample of convenience rather than any sort of random sample. Okay, so we like random samples. We honestly like something in addition to that. We like a uniform random sample, and that's where we will be going. Is there anything else I want to say? So yeah, you can get like No, I'll do that next. I'll do that next. So yeah, the next place where I want to go is, you know what? Let's stick with sampling for a second. So here, let me show you how to sample from an actual table. There's some stuff for that. It's dot sample. Here, if I go to the documentation here, we were using random.choice to get stuff out of an array, but you can just you can stick with the table and get rows of a table out randomly, and that is here somewhere. Should be just dot sample. There it is. Where was that on the left side? I did not see it. I want to find it now. Oh, it's an advanced table function. Table.sample. So you got some table, you say dot sample, and you can give how many things you want out of it, and it gives you that many rows, which is super nice. You don't have to go to an individual column, you can get the rows themselves. And it gives you back as a table what you get back. And there's also this optional parameter called with replacement. It's like, do you want to draw with or without replacement? By default, it's yes. I would like to keep replacing things, and we'll talk about what that means. But you can set that to false, and I'll show you the difference. All right. So it's dot sample on a table. It'll give you back a new table with pieces plucked out randomly sampled. That's what we like. All right. And everybody has an equal chance under that kind of sampling. So here, let's get the first 10 Pokemon just as a table by itself. So that's Pokemon. We know that dot take will give us a few of them if I give the indices. And so what are the first 10 indices? It's indices 0 through 9. Yeah. So I can see np.arange 10, because by default it starts at 0. So we'll go from 0 to 9 and take those first 10 Pokemon, and I can save that away so that we can draw from that. So those are the first 10 Pokemon. Those are the ones I care about. First 10. Boop. There they all are. And yeah, so we know how to, if I want to get some Pokemon names, I can get out the name column first. Be like, first 10, give me the column called name or column number 0, index 0, and then go np.random.choice with those. We'll remember how to use that first. And let's say I want 7 of them. All right. So by default, same idea here. There's do you want to use replacement or not? By default with these guys, with np.random.choice, it is with replacement. And what that means is there can be some duplicates. And it looks like we got lucky this time, didn't we? So let me rerun it. New random sample. Do you see how there are 2 Venusaurs? Sometimes that's not what you want, but this is called with replacement. Every time it draws randomly from this bag of 10 Pokemon, from this table of 10 Pokemon from the column, it's putting the one you just drew back in so that it has another chance of being redrawn. That's what with replacement means. So this one was with replacement. Sometimes you don't want that replacement. And the way, replace, that's how you spell that, right? The way you say that with np.random.choice, let me show you the difference between sample and np.random.choice. In theory, they should be next to each other, but I don't think they put them next to each other. Random.choice. That one says just, it's called replace equals true or false, not with replacement. So replace equals true is the default. We can say replace equals false to do this again. And this time, if I ask for 7 things without replacement, I will never get duplicates. I'm always getting 7 different Pokemon out of the table random. Does that make sense, the difference there? So there's a reason to want to do one versus the other, and I'll give you some examples, but I'm never going to get duplicates here. I am not guaranteed to get duplicates with replacement, but it's very likely if I'm taking 7 things out of 10. All right, very, very likely. So yeah, when you say I don't want to replace, then you do have to be a little careful, because if you ask for more things than you had in your table, 11 things, there are only 10, then you'll get an error, because it's cannot take a larger sample than the population when replace is false, but you can for sure do that when replace is equal to true, because it's fine with duplicates there, right? We rolled 100 dice, for example, it's always giving 1 through 6, or always heads or tails, that's fine. So you can totally ask for more than the size of your table if you're saying replace equals true. That's the default, okay? And so you can use np.random.choice to get a piece of a column, but sometimes you want the whole darn table, and that's where dot sample comes in. And you can say with replacement equals false if you don't want that, because again, by default, it's going to draw a random sample with replacement. And not just a random sample, it's called a uniform random sample where everybody gets the same probabilities. All right. So instead of saying get out the column and do a sample, do a random dot choice, I can say first 10 dot sample, give me 7 things. And this is what we get. Isn't that cool? So we get the whole table, and I could you can do table stuff now. It's great. It makes a brand new table filled of random rows, 7 random rows of the original. So that's great. By default, it is with replacement. You're going to have duplicates potentially. Okay, that is a possibility. You can turn that off, and that's with underscore replacement. Of course, it's not the same as the other one. They had to make it difficult. So you can say with replacement equals false. All right, and then you're guaranteed to, it's going to be random every time if I rerun it, but you're guaranteed to never get duplicates for that one. All right, so there's a row, or there's an array-based way, and now here's the table-based way of taking samples. And I think that is pretty much what I wanted to say about all that. So this is the new stuff. Dot sample on a table works very similarly to np.random.choice stuff. Any questions about that before I go to a different topic? If you want to get some random stuff, that is useful. We like uniform random samples. Let me just write that down here. Uniform random samples are the best. Equals love. That is my best drawing of a heart. There we go. So what uniform means is everybody has the same probability. That's what we like. That's what's happening in the table. Like this guy has the same probability, that guy has the same probability, blah, 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 on down the line. All right. So that's what we like to have, and that's what's happening when we're using our functions. But technically, a random sample does not have to be uniform. We just prefer it when possible. All right. So now I want to talk about distributions. Now that we know that we can have a random sample and like you just kind of have to know what the probability of everybody that could potentially be drawn from the random sample is, that's still a random sample at that point. Let's talk about distributions. All right, what that means, what this is, this word, right? It's trying to paint a picture of who's going to get picked and how often. All right, if you draw by random. So you've got some random quantity and you've got a bunch of values that it could be. So let's say like we want to know like the age of people in the United States or in the world, for example. And so we'll take like little samples, and you can have a probability distribution of all the different possible values of like the ages of people and the probability that they'll be that age. And I think you can imagine it's going to look something like this kind of graph, right? If you are, I don't know, or maybe a little different, won't it? It depends on birth rates and things. I don't know. Maybe it's more like this, actually, the probability of somebody being a certain age. Like age 0, you're just born, age 25, age 50, and so on. Like maybe there's just like a lot of people in this age, and then as you get older, it's less and less likely for people to be old, right? Like once you get past 100, it's almost a 0% chance that you'll randomly pick somebody who's 110. Like there's probably only a couple people in the world with that age. Does that make sense? Like you can assign a probability to everything, every value that you could possibly want to choose. And that's what it means to be a probability distribution. It's like a little graph that gives a probability to each possible value that you're trying to choose from, some sort of quantity, like people's age around the world. Like maybe there's a high probability chance that you'll randomly pick somebody who's just born, somebody who's like 25, and as you go down the line, like it's less likely for you to find somebody who's like 90 randomly. It's like that's a lower probability, something like that. You kind of see how you might read that kind of graph if I gave you one of those. So I'll show you plenty of examples, but like that's my best drawing of one that I can think of off the top of my head. And so yeah, there's a legitimate probability distribution of like the ages of people in the world. Like that we know that there's quite a few billion people. If we knew the ages of every single person in the world, we could make this exact probability distribution, couldn't we? Exactly. Because like we can calculate the probabilities of like me randomly picking somebody if I lined all 10 billion people up or however many there are. So yeah, if you can do math, if you count everybody, you can work out the probability distribution if you knew all the values. Or say you want to like roll a die or something. Sometimes you can like mathematically work out, or or let's just say flipping a coin, like heads or tails, you know that there's only two options and they have equal probability with a like a non-loaded coin. So like you can do the math and say it's 50-50 chance heads versus tails. Like sometimes you can work out the probability distribution immediately with some effort, stuff like that. But we really like to simulate things in this class. And so we're going to try to draw random samples and calculate these kinds of probability distributions. And if we draw enough things, enough times, we will approach the real distribution. Does that idea kind of make a little bit of sense? Because that's kind of our goal. That's kind of our goal for this chapter, most of the class, honestly. That's what we're going to be doing. So it's usually easier to simulate stuff. And so instead of like thinking really hard and drawing the distribution of like the coin flips, we want to create empirical distributions, the ones that are based on observations, like out in the wild. We're performing experiments, all right? So an empirical distribution is it's a kind of probability distribution, but it's not accurate. It's not precise, potentially. It was based on some random samples. If we took enough random samples, maybe it will be perfect, but at least it'll be pretty close. All right, that's going to be our goal. So that's the distributions in a nutshell. And let me give you plenty of examples of those with code. But do the words make enough sense to us? It's just like for every possibility, you want to find the probability of that thing, like that age, that outcome, that side of the die coming up when you roll your die. And so I think that's a good first example. Let's make a table of all the ways that you could roll a die. So with column, let's say like the face of your die is 1 through 6 if it's a 6-sided die. So np.arange 1, go all the way to 7 because it goes up to 6, right? 1 minus that. Increment by 1, so technically I don't have to give that, but like that is, oops. There's all the faces of a die, right? And I can call that die. All right, so that's one die. If you roll it, you get 1 through 6. Those are your possibilities. And you can, I don't know, you can take enough samples and try to figure out the distribution of like, all right, if it's a perfectly non-loaded die, every one of these should have an equal probability. So the probability distribution, like the exact one, kind of looks like this. So let me draw that for you first. So like you can make, the cheating way of doing this is to make like a little histogram. Make a histogram of all the values and give each one like exactly enough to space in between. So let's make all the bins of this histogram exactly 6 bins. Bins equals np.arange, exactly 6 of them, and they'll wrap around the 1, the 2, the 3, the 4, the 5, and 6. You don't have to understand what I'm doing right now. Just like 0.5 to 6 point, not 5, but 6.6, I guess, and go by ones. That's pretty much the probability distribution of rolling a die, right? That's exact. So I cheated and I used a histogram to generate this, but I hope you can kind of see the idea. Like, all right, the probability that you get face 1 out of all the others, there's a 1/6 chance, right? So 16-ish%, and that's exactly what it's showing, just by the way that I made this histogram. So this is the exact probability distribution of you rolling a random die, right? So perfectly not loaded. It's like 16% chance you rolled a 1, 16% chance you rolled a 2, or like almost 17% chance. They're all the same. Does that make sense? That's the probability distribution of rolling a die. Any questions about that? Because that's key to understand how to read these. Like that's the distribution. This is called a uniform distribution. All right. Uniform distribution. And that's where everybody has the same value. Everybody in this case is 1/6. All right. So that is our distribution for those die, for this, like for a perfectly random die. But let's make an empirical distribution. Let's try to generate, say that we didn't know that it was exactly this. Let's try to randomly sample from our sampling space here and see what we can get. All right, because I know how to sample stuff. I can say, all right, die.sample 10 or something. All right. Does that make sense? Like I can take a bunch of samples and like count how many 2s, how many 1s, how many 3s. Like if I took a large enough sample, like 1,000, 1,000,000 of this table, I think you can imagine it's going to start looking like this. Does that make sense? That's where we're going to go. Okay. So that is the goal. that's what's going to happen. And do I want to get there first or second? Let's see. I do have a question for you to try. I think I want you to try, and then I'll show you like how to think about it. All right. So I've made this die table, and here's how I made it. I made it from scratch. I didn't import anything. So like, please try to make this table. And here's my question for you. All right. So using this table, sample from it a few times with the dot sample. Let me show you that to you. Where was that? So like you can take 10 things. There's how you take 10 things. Boop. So that should be all you need for now. And that's going to give you a new table. You know how to work with tables, right? I'd like you to sample 10 rolls, get the average value. Sample 100 rolls, get the average value. Do it for 1,000 rolls, and do it for 1,000,000 rolls. And try to see if they're getting close to something. Yeah? Any questions about the question? Please go and try that. I think it will be very enlightening, and we'll make some graphs soon. I'm very excited. I don't want to do that. Plenty of time. Wait, 2 minutes or so, let's say. Please help each other. Good, well, I can help you. Get this cable back. And so we want to go in. I guess there's a couple ways to do it. But I would probably get the column out. Just be like, use my array stuff. Another minute or so. Oh, that is my timer. Let me fix what I'm doing here real quick. I think that's a better question. We can maybe do medium. Okay, are there any questions about the question as we were trying it? Do we get a value? Like what number did it get close to? Like when we got to 1 million, does it seem like it's approaching something, or is it just like doing some random looking stuff? I think it's going to approach something. Let's try it together. Let us see. So if I want 10, that's exactly this, die.sample 10. And then what do I want to do with that sample? I want to get the average value of this face column. So I'll probably just like go to column 0, the one and only column, and do like np.average, something like that. Is that what we did? I'd probably do something like that. And that is, all right, that's a decent number, 3.6-ish. All right, let's keep going. Let's do 100. Ooh, all right, 3.81 now. 1,000? 3.43. So it's kind of all over the place. But if you go enough times through the randomness, the magic of randomness, takes a while. It looks like it's approaching 3.5, which honestly, hopefully makes sense to you, because on average, it's going to pick as many ones as 2s, as 3s, as 4s, as 5s. They're all going to be equal amounts if you spread them out. Does that make sense? Like, that's how I want you to think about it. And like, what's the average value then of 1, 2, 3, 4, 5, and 6? It's right in the middle, 3.5. Does that make sense how it approached 3.5 now? Any questions about that? Because that's kind of what's going on. And you better believe that if we plotted a histogram of all the values that we saw, it would, for 1 million, look a whole lot like that. Does that make sense? That's where we're going next. So yeah, any questions before we go there? I'm excited. So yeah, that's what simulation can do for you. You approach the true thing with enough simulation. So you don't have to think really hard a lot of the time and calculate something difficult. You can just like let the randomness do the work for you, which is really, really cool if you think about it. So yeah, that's where we're going. It's called the law of large numbers, or the law of averages. And so here's just this could be from the book. I forget exactly where it's from. I stole it, but like this is a little blurb that kind of says that, and a cute little graph that shows you something too. I'll talk about it. It's like, if a chance experiment, so that's some sort of thing that we're doing that is left to chance. We're doing something random. If a chance experiment is repeated independently, like one run of it, one flip of the coin does not influence the next flip of the coin or something, like your thumb never gets tired. If a chance experiment is repeated independently and under identical conditions, then in the long run, the proportion of times that an event occurs, like a heads or a tails, gets closer and closer to the theoretical probability of the event. All right. So that's a phrase that will become very apparent soon. All right. So like what I'm trying to say is, like, if you flip 1 million coins or you roll 1 million die, it's still singular, right? No, 1 million dice, I guess, plural. Then you're going to get really close to 50% heads for a coin, 50% heads, 50% tails, and you're going to get really, really close to 1/6 chance of anything for your die roll. All right, that's where you're going. And here's a cute little simulation. Let me try to explain it. So this is on the x-axis. This is fun that I found it on the internet. On the x-axis is how many times a coin is being flipped randomly. And then here on the y-axis is the probability that you saw heads, let's say. Probability that you saw heads. So you flip a few coins, sometimes like initially I guess the first roll was tails, and so a 0% probability we saw heads. And then eventually, like sometimes you've rolled a few more heads than than tails, like it's jumping up to like 0.6, 0.7. And then as you're rolling closer and closer to 1,000, that average, the probability, the ratio of times that we've seen heads versus tails is approaching 0.5. Isn't that cool? And so that's what we get to bank on when we use randomness. We're always going to approach the right thing if we do enough. If we do enough, that's what the law of large numbers, the law of averages, gives to us. So yeah, let us compute now some empirical distributions and see this law in action. I'm very excited. It's called the law of large numbers, or the law of averages. And now I get to make pretty graphs. Get to do exactly what I said. Cool. Yeah, so let's do the following. So I did this kind of silly histogram before. I'm going to steal this, but I'm going to take a sample instead. This is like of the actual values. We know that that's the theoretical thing. Instead, I'm going to sample die.sample a few things like 10, and then I'm going to take a histogram of that sample. All right, so I'm going to take a sample. Here's a bunch of values for face. I'm going to take a histogram of how many 1s, 2s, 3s, 4s, and 5s, and 6s I've seen. So I'm going to make a histogram with exactly 6 bins in the same way as I did before. So that's essentially going to count the proportion of 1s, 2s, 3s, 4s, 5s, and 6s, because there's never ever anything in between. It's always going to be like the first bin's from 0.5 to 1.5. So it's just going to hold the 1s. Does that make sense? Because there's nothing in between. Then the next one's going to be from, 1.5 to 2.5. It's only going to hold the 2s. And so this is going to be a histogram of the proportions of these values. And look at it. For 10, there just happened to never be a 4. So it doesn't really look like the theoretical thing. Yeah, it was only 10. Randomness is still getting in the way of things. Does that make enough sense? Like for a small number, the law of large numbers does not apply. That's the idea. So let's make a function that lets us do this for any value of our sample size. Like this 10, let's make that be a variable. So instead of doing it just like this, let's make a function called, I don't know. I want to generate, this is an empirical distribution histogram. So let's call it def empirical histogram of like a die of, and then how many die rolls will there be? Let's say n. That's the number of die rolls. And so then I'll indent this and I'll say, hey, die.sample n things. Does that make sense? So I'll let that be a variable, whatever we passed. And then I can easily generate a bunch of these graphs for a bunch of different numbers. So like that's going to be my function. And so to redo what I just did, I can just call my function now. Empirical histogram with a die. I'm going to roll it 10 times. That's pretty nice. And notice that we get a different one because it's random. We get a different one, and that's what we see. So let's do it. Let's roll 100 dice, or let's roll the one die 100 times, however you want to think about it. Well, let's do it again. So I'm rerunning this function now with 100 to generate the histogram, and notice that it's starting to smooth out if you think about it that way. You can rerun it, of course, and it's going to look different because it's random, but you can see how they're getting there, right? They're kind of a little less wonky and all over the place than the first one. So the numbers are growing, the large numbers are happening. Let's do 1,000. See the difference in the spread there? That's interesting, right? It's starting to show the true color. So 16, 17-ish% is where it's supposed to be. That's the true theoretical probability distribution. And I've rolled 1,000 dice, I guess. I always never remember when to say die versus dice. But it's getting very close. All right, with 1,000, you better believe if I do 1,000,000, it's going to be even better. I don't know how long this is going to take, though. We'll find out. Got to generate the table. Look at that. It's a little, you can see that pixel's a little bit off, but it's pretty much there, okay? And so we didn't have to do any work, did we? Like, we didn't have to think very hard. We didn't need this, technically. We would have noticed that it approached that if we didn't know the true distribution. Like, just simulate, you can generate it. Isn't that so fun? I love it. Any questions about that? That's the law of large numbers appearing. We can do the same thing. We play the same game for a different kind of distribution because this is a uniform distribution where you have different values. There are some distributions that are not uniform. So here, let me show that to you. You remember our example from the San Francisco bike share stuff? So that's a different kind of distribution if we take like the duration that people were spending on those bikes that they were renting. So let's call that's the trips table, I guess. Table.read table data. It's this one, Bay Wheels trip data from June of 2025. And so here's all my stuff. It's a big table, so it takes a while to read it. I've got all these things, and I have the duration of like how long people were on this bike. And so a row per bike ride, essentially. And I can get, let's see, I can get a few different values like trips. Give me the column called duration, and then you can take the min. You can ask for that. So let's figure out, like, if I want to draw a histogram of all this stuff. Let's see what like the min and the max are. If you want to print a bunch of things at once, you can put them between commas. And then, all right, that's the min, the max, and we can do the mean as well, which is another word for average. And so it looks like some durations are almost 0 seconds because it's in seconds. Some durations are very, very long. Like, is that a day or something? Like they kept the bike out, or they just never returned it or something. They were charged for it. And then the average bike ride was about that much, 755 seconds, which is how many minutes? Almost 13 minutes, 12 and a half minutes. So let's make a histogram of like the normal amounts of bike rides. Like it's up to, let's go up to, I don't know, double this average or something. So let's make a histogram. I'll say trips dot histogram on the duration column, and the bins will be these ones. Let me generate a range of bins starting from 0, because like the minimum 0, up to, let's do 1500. But so I want to go to 1501 then by, I don't know, by 50s. Like every 50 seconds is a new bin. There is my true distribution. This is the actual probability distribution because I've counted every single bike ride. This is the real distribution of everybody who rode a bike in June of this year in San Francisco and rented it through the Bay Wheels program. All right, so that's the true distribution. It goes a bit farther that way, but I just put it on. But like you can see that is not uniform, right? A certain number of people were riding for under 500 seconds. Like that's the most populous area there. Yeah. So that's a different looking distribution, but it's still a distribution. Does that make sense to us? Still a distribution where people like they tend not to ride the bike for too long. And so say we didn't know what this distribution looked like. Say we did not actually have the data of every single bike ride in San Francisco. Say we just had a sample. We could still get close to this distribution. All right? And let's figure out how many people we would have to sample to get close to this distribution. Okay? So what I'd like to do is instead of doing it this way, again, I want to take a sample of the trips table. Dot sample a certain number of values, like, I don't know, 100. And then I can do a histogram of the same thing that I get out. So I've got a sample. It's still giving me back a table, right? With 100 things this time, only 100 different values. With repetition is important here. Dot histogram, the duration. And so it looks like that. Does that make sense what I've just done? I've taken a sample of the people who rode those bikes. And I mean, it's decent. I mean, if you think about it, it's got that spike, kind of where that spike really was. That's pretty cool. But let's turn this again into a function that lets me take a sample of a certain size. Let's call it n again. All right, so I'll call this. Oops, cannot run it yet. I want to make a function def. Let's call it an empirical distribution histogram for the duration. All right, where n is the number of is the size of my sample that I'd like to take, please. And so just for fun, I'm going to give a documentation string or a doc string with triple quoted things. We can say, what does this do? It creates an empirical sample and draws a histogram for it. That's kind of what we're doing. And so, yeah, I'm just putting spaces around the triple quotes for fun. But that's kind of what I want to do there. That's what's going on. There's my sample. And remember that there's also, in your histogram, you can say what the unit is, like percent per unit here, but the unit of duration is minute. So like we could say percent per minute if we like. Unit equals minute. And there's my little thing. So I guess I could have said that here too. Unit equals minute. Like that's the true histogram. But I can make another one based on a sample. So there's my function. Now I can call it. All right. Draw an empirical, take an empirical sample and make an empirical distribution histogram with 100 things. You still get the spike, which is kind of cool with just 100. But let's see what happens if we keep going. Like this is the true one. Say we didn't have the power to calculate it. We were just like interviewing people, asking them how long they rode their bike. How many things would I have to do before I had the actual values? Because there is like, sometimes this is not feasible. There's almost 350,000 different pieces of data in this table. All right, almost 350,000. That's a lot. It's like, but notice how if I just took a random sample of 1,000 of those bike rides, do you see how close I'm getting to the true sample? That's really powerful. It's very cool. All right, and of course, if you rerun it, you get a different sample, but you can kind of see the shape the more you do. All right, we'll do 10,000. Even if, like, they're a private company, they only want to give away 10,000 bike rides, you get very, very close to understanding the shape of all 350,000 bike rides for the month with just 10,000. Isn't that so nice? Any questions about that? That's the law of large numbers appearing. So that was large enough. Cool. Yeah, I think that's most of what I wanted to say about that topic. Any questions before we move on to something slightly different? Because we're still going to stay with this idea. It's just we're going to a different kind of place. So, like, it's now my turn to talk to you about statistics, like the actual idea of statistics, because that's kind of what data science is. In my opinion, the idea of data science is it's just a buzzword. It's just a rebranding of statistics. So that's kind of what we're doing in this class secretly. And so I need to teach you actually what statistics means, all right? Because our goal, kind of in this class, is to do inference. We have a small amount of data. We'd like to glean some information from that data to make our company money or something like that, all right? Or to do something better. So we want to infer things from a small amount of data, just kind of like we're doing here. From a small amount of data, I'd like to infer something about a large population. All right, that's what I want. Like, if you work for TikTok, like, what is the best way to keep people addicted to their phone? Something like that. Like, that could be, somebody cares about that, all right? And you can think of a nicer topic as well, a nicer idea. But we want to do inference, specifically statistical inference. We want to use numbers, right, and make some important conclusions and have numbers to back them up. So statistical inference is just the idea of making conclusions based on data in some random samples, all right? That's what we want. So an example that I've already kind of given is the idea of like, all right, let's randomly sample some students on campus in a nice random way, not just like everybody out this door only, because maybe there was a certain class with a certain age of students. Like, go all over, ask a bunch of people. If you randomly sampled a bunch of students on campus to guess their average age, that's the idea of statistical inference, all right? If we took a random sample, it will help us estimate the true average age if we were to actually get the I doubt the school would let us have it. There's probably some laws against it. But like, if you got the list of every student who goes here, you could compute the real average age. But we can get pretty darn close if we randomly sample some students here on campus. Does that make sense? That's what we can do. And so we can infer things in that way, right? So the average is a statistic that we could calculate, and we can go from there, all right? So let's actually talk about the difference between statistic, because there's something that's very similar that's the same idea, but different, all right? And so I always mess these up. I will forever mess these up. Please correct me. Let's go back to this picture. So remember, our goal is like we have some large population of people that we want to deal with. We want to infer something about them, like their average age, who they're going to vote for. Like the population could be the U.S. citizens, people of voting age in the U.S. That could be the population. Just like everybody in the world could be the population. You're never going to talk to all those people. You're never going to get what you want from all those people, so you take a sample. All right? Say you wanted to know the average age of everyone in the world. All right? That is not technically a statistic because it's dealing with the entire population that you're sampling from. So that's where this word comes into play. So that would be called a parameter at that point. There's a difference. So a parameter is when you've got data from the entire population, like you do have every value. A good example of a parameter is like when the U.S. Census happens. Like the U.S. legitimately sends mail to everybody, every household in the U.S. They're trying to actually calculate and get data back from every single person. That would be like a parameter, even though some people don't respond. So they still do have to do statistics, but a parameter is a number associated with the entire population. All right. So like, if you could have a list of all the billions of people on Earth and take their age, take the average age, you would have calculated a parameter because that's the true value. All right, that's the true value associated with the whole darn population. When you take a sample and you take the average age, that's your statistic. That's the thing you're trying to use that to infer the parameter. All right, so a statistic, the technical term statistic, just is a number calculated from a sample. All right, there's a huge, huge difference there. Population versus sample. So the average age over everybody on Earth, if you could have that value, it's a parameter. The average age of like you sample 10,000 people on Earth, that's a statistic at that point. Does that make sense, the difference there? It's very subtle. Like parameters collected from the entire population. Statistics collected from a sample. All right. And the reason that we have statistics is that it's usually infeasible to calculate the true parameter, but we would like to estimate it. We want to estimate our parameter using some statistic. Okay? They go hand in hand. And that's our goal. So those are the technical terms. If you've never heard those before, now's the time. So I hope that makes a little bit of sense. Are there any questions about that? Just the terminology. I'll try to get the words right. Please correct me if I get them wrong. But yeah, kind of our goal is like, okay, we want this statistic, like we want this average age, we want this median age, right? There are different kinds of numbers that you could calculate, the max, the min. Those are statistics if they deal with a sample. So the values of your statistic as you're taking your sample and trying to calculate something important to you, they're going to look different every time. So for example, like this 100, take 100 things, draw the thing. A different one is different because it was a different sample, right? And so you better believe that if I took the average duration from this sample and this sample, it's not going to be the same one, right? It's not going to be the same exact number because it was a different thing each time. So the values of your statistic, of your average duration, whatever you're trying to calculate, they vary because the sample varied, right? It's a different sample. It was random, the one that you got. It would be random the other if you tried again, right? It'd be a different kind of distribution probably. And so if we could know this, it would be nice. This is kind of what our pie in the sky dream is, to get the true probability distribution, or another word for that is the sampling distribution of the statistic we're trying to go at, like the real, like every possible value of the duration of your bike ride and all the probabilities, like the true stuff. That's kind of essentially this all over again, the real true thing. It'd be nice to have that. But it's very hard to calculate it exactly for most things. Like sometimes it's very easy, like you have all the data, or you have that it's uniform, like your dice, your die, it's all the same. But a lot of the time we cannot calculate the true probability distribution. We cannot do it for a statistic that we care about. This is just what we've done is just over the values, over the face values, over the duration values. Where we're going right now is like, let's actually take the average of the sample. Let's calculate a true number, a true statistic, because this is just looking at the sample in a random way. Once you start calculating the statistic as well, you would again want this. Like what's the average I'll ever see? If you want to think about it that way, it's going to be difficult and weird to imagine, but it's again hard to calculate exactly, just like it's hard to get the exact values for these distributions, but with enough samples, it'll start to approach the true distribution. All right. So again, we want to calculate an empirical distribution. That's the easy thing for us, of a statistic now, like of an average. So like take a sample, compute the number that you cared about, like the average age, the average duration, something like that. And then you're simulating that, all right, rather than just like drawing graphs. So an empirical distribution of your statistic is based on your simulated values of that statistic. So think average now. Don't just actually think about graphs and the sample itself. Like do something with the sample, the thing that you wanted. Like I want the average age. I want the median duration. I want the max. I want the min. So this slide is essentially me talking about us doing everything we've just done, but with a number now, with the statistic that we cared about, not just the actual values of our sample. Okay, I hope that distinction makes a little bit of sense. It is very, very subtle, and so I'll give you a good example in just a second. But that's the idea. And so again, you can imagine that everything that we've just done applies still. It's like if we do enough, right? We want to calculate this true probability distribution. We want a good approximation to it. We want a good estimate of it. The probability distribution of the statistic that we care about now, like the average, the median. Again, the law of large numbers applies. We can get a good approximation. We can calculate an empirical distribution of our statistic if we do enough repetitions, if we do enough, a large enough simulation, 10,000 times or something important, something large, more than just 10. Okay, so that's where we're going. That's what we want, and we're going to get, with a large enough sample, we're going to get a pretty accurate drawing of what we want, even once we start going to statistics land. Start calculating some important number based on our sample, right? Because that's what we haven't done yet. Everything that I showed you here, it's like we're calculating a number, like we're looking at our sample itself. What statistic means is we're trying to calculate a number based on our sample, all right? That's where we're going. We're trying to do inference. So where should I write that? Like we don't just want to take a sample anymore. We want to calculate some number based on our sample. We want to calculate a number based on our sample. I don't know if this is the right slide to write this on, but this is important knowledge, right? Based on our sample. That's the only new thing for this little subsection, right? That's what we want. That's the difference between this and the other pictures I've drawn. So yeah, again, if your sample size is large enough, then your empirical distribution, the one that you get through sampling of a uniform random sample, it resembles the population distribution with high probability. So this is just another graph. Don't worry about what it's actually trying to do. But like the green thing is the true probability distribution, whatever thing it's trying to whatever it's trying to be. And then the blue is like what your sample drew, what you got from the sample, how you estimated the green line from the sample. All right. And so you see that it's wonky when you take a small sample size. So n is a very common letter that's used to mean sample size. It's 25 there, 100 here, 1,000 here, 5,000 there. And you see that it's just pretty much on top of this thing that it's trying to simulate. That's beautiful. So like law of large numbers still applies for the value of a statistic. And just again, the idea of a uniform random sample, I said it enough, right? But uniform just means everybody has an equal chance of being picked. That's the difference, right? So everybody has an equal chance. And also that means with replacement, right? It's just like you're rolling a die. You don't like, once you roll a 6, you don't scratch off the 6 from the die, all right? That's what it means to be uniform random sample. You can get the same thing twice. It's still random, okay? So I think that's what I wanted to say. Yeah, are there any questions before I show you some graphs? So I want to calculate statistics now, not just take the sample and see the spread of the sample, because that's what we were doing. We want to actually calculate a number now. Empirical. And then we can graph that though. So there is a subtle distinction there. Empirical distribution of a statistic. Boop. So that's where we're going. So let's do the trips. I think that's a cool little table. So like I got my trips table of like 350,000 different bike rides in San Francisco. Let's see what's going on there. So I can say trips.column, give me the duration column. Like this is going to give me every single duration, all 350,000 of them. And you could calculate some value, some statistic based on, well, technically now it's a parameter. The trips table, I have everybody right now. So this is a parameter, technically. We can calculate the average, np.average, np.mean. Like that's the average. You can also do the median. Like that's one we haven't really done yet. So like the median value, it's a little bit different. Cool. So let's do that. So this is a parameter right now. So like this is the true value of the parameter. All right, because this is the entire trips data. All right, I have it all to me. If I just had a little bit, I would be calculating a statistic, not a parameter. All right, so the difference now is I can do it this way. I can be like, all right, trips, let's take a sample out of those trips. Let's sample 1,000 trips, right? Get the duration column of those 1,000, take the median now. You see the difference there? That's a sample now, and it's kind of close. That's kind of nice. So that's the original one was like I used every trip. I calculated the true value of the parameter. This is just a statistic now. This is through the sample. This is a statistic. Statistic. Okay. And you see how you rerun it as a different random sample, but it's pretty darn close most of the time, which is kind of cool. So I just took 1,000, and it's within 10 seconds of the true median, the true parameter. I've estimated it very well with just 1,000 things. Does that make enough sense? So that's the parameter. That's a statistic I've calculated from a sample, trying to estimate the parameter. Any questions about it? Because that's a key thing. Like that's our job. That's what we want to be able to do in general. So yeah, let's do that. Let's again, because you know that if I rerun the cell, you watch me do it, this value is going to change. This value will never change because it's the value of like all the things. But you take a new sample, you're going to get a different value. And so now the question, the age-old question is, how bad could it be? How far off could I be with my 1,000-sized sample? Okay, does that question make sense? Because sometimes it's a good value, it's very close, but through randomness, sometimes it might be off by like a minute. We don't know. So we can try to determine that spread. Like how far off could it be? And we're going to see something interesting. All right. So let's do this process of taking 1,000 sampling the trips table 1,000 times, taking the median. Let's do that a bunch of times and see like all the different kinds of medians I can get from a sample size of 1,000. Okay, that's my goal right now. So I'm going to make a function that I call it gives me back a median. All right, of a random sample of size 1,000. So let's call it random sample median. And every time I run it, it's going to return to me back. It's going to take this. It's going to take a sample, size 1,000, give me back the median. So I can just rerun this function very quickly. Does that make sense what I'm doing there? It's like, I'll just run it, random sample median. Boop. Every time I run it, it gives me a new value back, and so I can just repeatedly run that. Okay, that's what I'd like to do. See how far off it could be. You see how now it's pretty low compared to the original parameter. So, yeah. Sometimes you're not going to get the parameter value. You don't have it. Like you want to talk about everybody on Earth or something. So let's make an array of all the different medians I could get back. Medians equals just a blank array. Make array with nothing in it. And then I'm going to, let's say I want to loop 5,000 times. Just it's a number we made up. So for I in np.arange 5,000. So this I value is going to range, between, the I value is going to range between 0 and 4,999. I'm not going to use the value of I. I just want to run the body of this loop. The inside is called the body, right? I want to run that 5,000 times, and this will let me do that. And so what I want to do is say, all right, every time I'm in the body, I want to call this function to get a new median back. And I want to add it to my medians array. I'm going to add it to the end by appending it. So medians equals np.append. You got to call it like a function. Give me the old one, medians. And then here's the new thing I want you to add to it. So it generates one longer array that didn't change the original one, and then we set it right back into it. So this is going to let medians get bigger and bigger and bigger, and those are what we're seeing there. All right. So it'll take a second to run. You see, it's still thinking. And this medians array, once it's finished, is going to have 5,000 different median values. All right. So this will take a second to think about, but like that's what we're getting, and we can make a table of what we get back so that we can like look at it in a pretty way rather than just looking at the array, and that will let me do a histogram of it. So like let's make a brand new table with those values in a table dot with column. I'll call it sample median, and I'll put all the medians in there, and I'll call that simulated medians equals that simulated medians. And this is, oh man, should I have done 5,000? I don't know how long it's going to take. But it takes some work. Like it's not the world's fastest thing. It's thinking really hard right now. How many times is it taken? Because like the trips table is huge, right? It was very large. So that's what happened. And so there's my array. It finally finished it. Because it had to take, like it was 350,000 big. Like it had to go through all that. It took a long time. But it's finished now. And so now I can make this table just in a pretty way, putting all those same values in a column of a table. All right. So like here are all the different median values. Sometimes it's big, 546, 562, but you can kind of see how it's kind of centering around the true parameter, which is kind of neat. That's important. And so here, we know that the true parameter value is about 555 seconds. Let's do a histogram of all these simulated medians now that I have it in a table. Simulated medians dot histogram of its sample median is the name of the column. But honestly, there's only one thing. So I can say, I guess it's fine. Let's say column 0. And you get the default 10, which is not really good enough. Let's make a histogram just with the default begin and end, but let's have it do 50 bins total. And that's kind of neat. You can see that most of the time that we took our sample, we got very, very close to the true value, which was 555, the true parameter value. Our sample, like, randomly, usually gets to be about there. Does that make sense? It's very unlikely that when we took 1,000 things, that we got something very far away from the true mean. You see that? Sometimes we did. We got all the way down to here, but we didn't get any farther away. No down past 500 seconds, no past 610 seconds. That's about the edge of it. And so that's decently precise. But do you see that sometimes you will be thinking that the value is a lot less than it really was, and sometimes you'll be thinking that the value is a lot bigger than it really was. Does that make sense to you? That is important. It's never going to be perfect, but you do it enough, it will approach the true value. All right? That's kind of neat. And so it's kind of just falling off around the true actual median, the true parameter. All of our statistics are getting close, usually. So that's kind of neat. All right? Any questions about what we just see there? Because that's a very powerful thing. Very powerful idea. All right, all right. What else do I want to say about that? I think that was most of it. And so I just want to prove to you that that is not a fluke. So here, I thought of an example, but we kind of actually already did it, so I made a new example while you guys were doing a question. So here, let me bring it in real quick. Boop, boop, boop. I want to do this one. And not the Titanic one. So we kind of already did a Titanic one last slides. So here's my example for you now. I'm going to give you all my code in a way. Here's essentially what I just did. I want you to do kind of the same thing. We do medians again. We're not used to that. But you can do it with average if you'd prefer. If you finish early, maybe you can try that. But what I'd like you to do is the following. I'd like you to make a function that does a sample of, let's say, 100 max temperatures of days in Fresno. All right, so that's going to be this table. Go and get that, please. It's going to be, I think it starts with max min temperatures, Fresno, up to blah, blah, blah. So go find that. Let me read that in for us so that I can just show it to you real quick. So I'll call that temps equals table.read table data max min blah, blah, blah. Temps. So there they are. Let's do highest highs. All right, let's do max temperatures. So highest high temperatures. Let's call it that. Highest high temperatures. And let's say you get the median temperature in that sample. All right, so very similar to what I did, but it's just 100 this time. I'd like you to take that function that you made that gives you back a median value for your sample of size 100. I'd like you to run it, please, not 5,000 times like I did here, but do it 10,000 times so you can see the difference. And save each, let's do median estimate, and try to see what the spread is. You can also calculate the actual parameter value, right? Because you know you can take the entire column and get the median, the true median, and then you can see how yours compares. All right, so maybe you can do that. Compare against the true median and plot the estimates with a histogram. That is my goal for you, and I think that will be fun. Are there any questions about that question? Think you can do it? So please give that a try. We got plenty of time, and I will be here to answer any of your questions if you have any. So just 100 days in each of your random samples. I think you will notice something cool. Can we scroll? Have you made any graphs in this again? It could be like the last time you opened it, there's something special about like that part. Those are not enough. Where's the last time you made graphs? Scroll up to it. Like you said all those before. Probably not. Yeah. So scroll up because it's something called like it starts with a percent sign. Not when you say something like the word inline, is all that. Like that part of the incantation at the top. Yeah, plot word. Those things. Those things. That's saying whenever I try to make a graph, don't like export it to some file or something. Like put it in line with something. So that's what you do. Yeah, if you finish early, I'll give you another 2 minutes or so. Try the average. Do the same thing with the average. See how it compares. I think you'll notice a pattern. Another minute or so to try. But you know how to calculate the true median as well, right? See how it compares? Is it going to center around? Are your samples going to center around it again? I think so. All right, I think that was my timer. Are there any questions before I do it? Did it make enough sense? Did we get a value? Or a pretty graph, at least? All right, let me try it, and then I might want to do something special afterwards. We'll see. So, okay, we got the stuff. I want to work with highest highs. So, how that works is, well, let's take a sample. We can get a sample of 100 rows of this table very easily. You can just be like temps.sample 100, right? Temps.sample 100. So there's 100 different things, and I can get always the median temperature of that sample by going to the column highest high. So it could be, you can spell that out, or it could be like column 1, right? Give me that column, and then you can do the median, like we were doing up here, is np.median over that. np.median over all that. So apparently it was 94 this time, 91 this time, 95 that time. Okay, so those are those values. Does that make sense so far? That's how you get them. And I just want to make 10,000 of those. I want 10,000 estimates, please. So I can essentially do all this over again. I can be like, make a function that does this for me, def. Give me a random sample median. I could redefine that function, I guess, if I wanted to. Random sample median, and I can call it like that. And so now, excuse me. Just a few more minutes. I need to keep my voice. All right, let's say random sample median. And now I should be allowed, oh, sorry, I have to return the value. Excuse me. And now every time I call it, it's a different value. So it's doing the work for me. It's a simpler name now. It's less typing for me. So now I want to loop through that. Like, let's make another array and call it medians again. Start it empty. And then every time I call this, I want to add it to the end of medians. Like medians equals np dot append, right? Append to the medians array this new value that I'm getting. And I want to do that 10,000 times, so that'll be a loop for I in range 10,000. Right, so that'll loop 10,000 times. So I will go between 0 and 9,999, but that doesn't really matter. I'm not using I. I get all that, and now I have that array. Once it's finished, it should be decently quick because it's a smaller table than the other table, but it's still pretty large, I think. So there it goes, it finished. And now I've got in this medians, array, I've got a bunch of different values, 10,000 different estimates here, and I can, let's see, first of all, we can calculate the true median very quickly, right? We can say, what was the true median? It was the np.median over the highest high of the original table. That's if we didn't sample, right? Just take the original table. Apparently the median is 96. Very hot median temperature for Fresno. But now we can do a histogram of our medians values by putting them into a table. It's like table dot, like a blank table with a column for all the different values that I see here. What did I call it last time? I think I just called it sample median, right? With column, I don't know, sample median again. That's fine, and it's medians. So there's the table, and then once you have a table, you can say, give me a histogram. Give me a histogram of the 0th column, probably with more bins than we want here, than we're getting here. Be like, give me 50 bins, please. Maybe that's too many. Give me 25 bins, please. Something like that. Yeah, that's kind of how that looks. Give me 15 bins. So it looks like due to the way that these values are kind of spread out, it's not as pretty, which is interesting in itself. It's not as pretty as the original ones. But you can kind of still see that the max thing, it's still pretty centered around the true median, which was 96. Does that make sense? So that's what's going on there. That's what we're getting. Yeah. So that's pretty neat. That is very, very neat, I think. And let's see, what else do I want to say about this? I think that's most of it. You could have changed which size sample that you used. Like sometimes, like we can do all of this all over again for a different sized sample, and like that might change how it looks. Like take a sample of size 50, something smaller. So maybe let's change this function to take the sample size. Sample size, just call it that. And then once you've done all this, just like immediately make, I don't know, this table and draw the histogram. Like we can make this happen in another function. Let me show that to you. It's kind of weird. So let's do that maybe. I think that, no, it could be fine. This could be fine. So like this is doing everything all over again at once with a different sample size. And so if I set, I guess if I wanted to do it that way, I could have just done it like this. I could have set the sample size up here. That's probably the easiest one, like 50 instead of 100. Like how does that change things? Let's see. I was doing all those things all over again with 50. That's a little different. Maybe a smaller sample makes it look cleaner as far as the histogram's concerned. Take 25 things. What do we get? The smaller your sample, though, the more likely you're going to get weird values, like you took only the cold days, only the hot days. So you see how it's like it's spread out now that I took only 25 size sample, but take a 50 size sample. It's going to look a little different. And I might as well show you all of these. So let's redo all this. I do think I want to turn this into one big function that does all this at once so that I can keep recalling it. Because I want to rerun this code a bunch of times. It's got a function in it already. I can turn it into its own little function. Let me show that to you. It's really weird and kind of cool to think about. So let me make a new function called, I don't know, what is this process? Calculate sample medians, calculate and graph sample medians. And graph sample medians with a given sample size. Look at what I can do. This is going to make you feel a little uneasy. Well, I can indent all of this. Because what is this but code I want to run, right? Whenever I say this name and give a sample size, it'll have a value, and it will use that sample size in this inner function definition. Does that make sense? What's going to happen if I run this code? I'm going to do all this over again. I have to call it like this now, and I give it a sample size. So it's just a function now. I can say, hey, do it with a size 50 sample. It'll run all this code where sample size is 50. It will redefine this function and only use it where it's 50 because sample size was that, and it does all of this all over again. So I can recall this to make a bunch of brand new graphs. Does that make sense? It's so weird. It's doing all of that at once. It's got a function inside of the function, but it's okay. It's okay. It's using that value from the outer one. It's very, very cool. And so I can keep recalling this, right? With size 50, of course, it's going to depend. You're going to get different things. It depends on the sample. But like the true median was 96. You can see it's there. With a size 100 sample, maybe ours was a fluke. It looked a little weird just because of randomness. I think it did. So you can kind of see how it's a little more curvy that way. If you took a really small sample, like only do 15 days or 25 days or something, maybe you just got all the winter days now. See how it's like sometimes the median was down in the 70s. Sometimes it was, maybe you took only the hot days, it's up in the 110s. These are maximum temperatures though, records. So that's kind of interesting. If I took even more, like 200 days, then it would stop being so spread out. It would get closer and closer to the right values. So that's kind of cool to think about, I think. It's taking more values, and so it's going to look like that. And so, yeah, it's going to be spread out in that way where it's going to get just spikier and spikier, closer and closer to the right one every time. All right? So that's kind of cool to think about, I think. And yeah, a lot of the time it's supposed to be like a perfect little curve like this. Like this. But I think just because of the way this data was generated, like it's only whole number values, it looks a little wonky. But that's okay. That's our distribution. That's how it kind of looks. It's still very close, and it falls off on the edges. And it's got the spike in the middle with the true median. So yeah, I think that's what I wanted to say about all of that. Any questions about this question? All right. So if we did that with the average, just for fun, very quickly, what would change? Calculate and graph sample averages. It would just be NP dot average. That's the only difference. You probably don't want to call it medians anymore. Averages, AVGS maybe. But that's a very quick change. Sample averages. Like I've changed a few things, just a few lines. It's like the main one was this, and just a bunch of variables. So how does that look? Well, let's find out. Do the same with the averages, and that might be a bit, because the average is very nice and smooth. That might be a bit better, honestly. Whee. And that will be the last thing I show you. The average is nice and pretty and smooth. That's kind of interesting that the median wasn't. Just the way that it's calculated is a little bit different. So that looks more nice and falled off from the true, which is probably 93 or something. Cool. So yeah, that's what I wanted to show you there. Maybe it would have been more entertaining to do the averages, but that can be a job for next semester. Any questions about the question? So you can ask a lot of things. You get a bunch of statistics, and you can create an empirical distribution of that statistic. Important, interesting stuff. Usually it's going to look like that. That looks a whole lot more like this guy. That is a very important graph. The medians were a little weird because they're calculated in a weirder way. But that's kind of neat. Yeah, because we didn't have a lot of data, I think. So there's that. There's really just one last thing I want to show you. Are we ready for it? For this chapter? There's a nice little function that was given to us, just like outside of table land, outside of NumPy array land. It will give you back, like you give it a probability distribution manually and a sample size, and it will draw from that distribution in a fun way. So I'll show that to you. It's called sample proportions. It's over on the side somewhere. It's probably in the advanced section. There it is, miscellaneous functions. Sample underscore proportions. It's a little weird. You give it a sample size first, and then you give it an array or a list with those square brackets of model proportions, and this always has to add up. The array or list here has to always add up to 100%, so 1. It's saying like the first thing has probability 0.5, the second thing that you could possibly pick has probability 0.3, 30%, and then the last thing that you could possibly choose is has probability 20% or 0.2, so use it in that way. And I want to draw 100 things randomly from this sample, and it gives you back like, all right, you drew 32% were the first thing, 32% were the second thing, 36% were the third thing, which honestly doesn't look right given these probabilities, but it was just 100 things. So let me kind of show you what that's doing and why it's useful, because it would be a lot more painful to do this manually. So let me show that to you. It takes an array of model proportions and a sample size. So let's just make a new section for it. Sample proportions. And so let me do something that's very tedious. All right, let's be like, let's make a table that represents all the ways that a coin could be flipped, right? Table with columns. We've got, we'll call it the face column. Like, what is the face of the coin? It could be heads, or it could be tails, right? So there's my coin table. And then, like, everything I'm about to do is very tedious. That's the goal, to prove that to you. The following process is very tedious, is tedious. And so there's my coin table. It's got heads and tails. Face is the label. Let's say I want to flip 100 fair coins, right? I've given 50% chance heads, 50% chance tails, because those are the only two options, and it's going to be uniform random sample. So coin.sample, 100 of them, please. So there's my 100 coins I just flipped. Heads or tails, 100 heads or tails. And then I want to count how many, like what's the proportion of heads and what's the proportion of tails from this sample. So I can group to get that, right? I can group by the face. That's the only thing there, right? Face. Group by the face. And there are my counts, right? If I want a proportion, I could go in and say, give me the column called count, and then I could divide by the sample size, right? Because I can do that kind of math on an array. There's a by 100. And it looks like for this particular sample, it was 46% the first thing, 54% the second thing, and I honestly don't remember what the order was. Probably alphabetical. Heads, then tails. Yeah, so it was heads, then tails. But you had to remember that. And it's a different sample every time. So like this time it was 55% chance heads, 45% proportion out of this sample was tails. So does that make sense how you'd want to do that sometimes? Like I want to roll a fair, flip a fair coin and give 100 times, give me how often, like a proportion it was heads, proportion it was tails. That's something we'll care about doing. So you could make this setup, you can make the table, you can keep asking it to do things for you. Like you got to make the table itself, that you can sample from it and group and count the things. And every time it's different, right? So cool. Sometimes it's the same, sometimes it's different. A lot of times it's the same here. There we go. Good enough. And yeah, that whole process took a while. I can do this entire thing in one line with the sample proportions function. That's the goal here. That's why it's cool. So I can say this instead. Bless you. I can give the distribution of how a coin works. I can say distribution equals make an array of all the probabilities, right? There's for the first one, say that the first thing means heads, 0.5 for the first thing, 0.5 for the second thing. They add up to 1, there's my distribution. The first thing, let's assume the first thing's heads, it's 0.5 probability. The second thing, tails, is the other probability. You could also have given this as a list. So like list 0.5, 0.5 with the square brackets. It's also a sequence. Would work here too. However you want to do it. And then you say sample proportions with, like I want to do 100 samples, please, from my distribution. And so this could have gone right there. I didn't have to make the extra variable, but like that is that entire process. So much less typing. Isn't that nice? And you just remember like which one was first. It's like the first thing meant heads, the second thing meant tails. And of course, if you rerun it, you get different values. It will be exactly the same kind of, ooh, this time was exactly half and half, nice. It'll be exactly the same as the other one. All right. So yeah, that's why you would want to use it. It's so much faster to just like, all right, the first thing means head, the second thing means tail. Just keep that in your mind, then you run the function. Okay. So yeah, that's what it takes. It takes the sample size and the distribution that you want to draw from as a sequence of all the probabilities that of each of the things in that distribution. Okay. So for this, it's exactly that. Cool. And so you could have sampled more things, less things. Makes it very simple to do that. Like, all right, do it 1,000 times. We'll get closer and closer to 0.5 for each, because law of large numbers applies. And I think that is pretty much all that I wanted to say. Are there any questions about this function? It's neat. It'll be useful one day. And I think that's all that I wanted to say about this chapter. Any other questions about anything else we did today? So we learned how to make some very cool stuff. So like the different kinds of samples. We want to take a statistic from the sample and see how it like compares to the original parameter. Because most of the time, like we were nice. We had actually the values of the parameters in these examples. Like we had all the data. But usually in the real world, we will not have all that data. We're trying to see how, like, you know, we didn't have to take as many things as we thought. Like we will get very close, usually, if we just had a small sample size. And so we can quantify that later. But like that's pretty good news, I think. Okay, so that's where we're going. And yeah, the last thing I want to say is that we can now have a due date for this lab 5, because that depends on this chapter. And so let's figure out when that's going to be due, and then I will let you work. Another thing that I do want to talk about eventually is our midterm. Our midterm is going to be week 9, so it is 2 weeks away. I will talk about that on Wednesday. Okay, I promise to talk about that on Wednesday. But yeah, let's figure out when to have this due date for lab 5, and then we can be finished. Oh no, I have to log in. let's see when things are due, and I'll pick a day where things aren't due yet. So at least a week from now, I would like to have this due. Is that doable? It looks like there is nothing right now a week from today, so that I think that can be the due date. Is that fine? That sound good? Make sure you're doing project 1 because that takes some time. Like that will be due next week as well. But yeah, we'll do Monday the 29th will be when lab 5 will be due. Okay. So we'll do that. I think that should be fine. What's the week after that? So that's week 8. Was that a question? Yeah. No, it's not next week. Week 9. We are in week 7 right now. We're in week 7 right now, so it's 2 weeks away. The short story that we'll talk more about next time is going to be on the Wednesday of week 9, so it's going to be on the 8th of October. So that's when we'll talk more about the topics and everything next time. Honestly, I feel bad because the project is kind of involved. So I wish I could see multiple things. There's nothing due after that, right? When is the... Let's see, then you got the midterm though. So that's difficult when to have this due because I want to test you on this stuff. Let's do, I don't know. Let's make it due on Friday after the project. I think that would be a better idea. So you can get the project. Let's say that it'll be due next week on Friday, this lab 5. Does that sound good? I think that would be less evil. So that's when it will be due, and I will remember that on the 3rd. Oops. I'll deal with that in a second. But yeah, any last questions about anything you want to talk about before I let you work? Yeah.
Is our midterm going to be like a paper thing?
It's going to be on the computers, but you're going to treat it kind of like a paper exam. So I'll talk more about on Wednesday, but you will be allowed to use that little website. I'll give you a list of allowed websites, and one of them will be that little temporary Jupyter notebook. Okay? So it's not quite on paper, but we will talk more on Wednesday. Okay? Other questions? Yeah.